Hello everyone, I have here what I think is the final version of my radiation shielding designer. It's called Reactor Systems Designer, but it's mainly to design the shielding for reactors in space so that the radiation doesn't harm the crew. And we have a lot more options, and I think it's a lot more accurate than the previous versions that I have shown. So I'll be sharing this in the video description. It is called Reactor Designer version 4.1c. And this was produced by going back and forth between Claude AI and ChatGPT, and then me injecting my own observations when I thought that numbers were not going in the right direction. So basically, Claude did the programming, and then I brought the script, the HTML file, over to ChatGPT and asked ChatGPT what was wrong with it. And the ChatGPT would give some suggestions, and then I brought that back over to Claude. That was the main thing, and then again, occasionally I gave my own suggestions for what could be improved. So that is what we have here. And in the process of ChatGPT nitpicking about this, it forced Claude to add all sorts of caveats to things, including, for instance, the fact that if we turn the power down, it gives a warning that says outside valid power range, because now we have fusion reactor options, but fusion reactors don't operate at low power. So it has to be above a certain power, thermal power, for there to be fusion happening. We have the fission reactor types. Those are the ones up here, and they all emit different kinds of radiation, and same here. But yeah, there's all sorts of little caveats added here to make it more accurate. But don't worry, we can collapse these things. Once you've decided on your reactor type, you can collapse that. And then here we have shield position invalid, because the reactor is large enough that the thing is, it's measuring the position of the shields with relation to the center of the reactor. But if the reactor is large enough, then the position doesn't make any sense. So we have to move stuff further away. So position from the reactor, we move away, and then it's okay. So there's conditions like that. There's lead, tungsten, depleted uranium, and steel for the primary material for the gamma and X-ray shielding. And then you have the thickness, and then there's a borated polymer layer directly on the X-ray and gamma shield, and so that can adjust things. But that doesn't affect these. This is just the scaling stuff and the positioning, but we really want the radiation tab. And here we're pretty good. The thing is, I've selected a reactor type that is aneutronic. So there's near aneutronic. It says proton boron 11 emits very low. That's the good thing about it. The bad thing about it is really hard to make that kind of reactor. But let's make something that, that's a fission reactor. Well, it's giving a whole lot of radiation that we will need to deal with. Of course, this is with 29 megawatts. Perhaps we should scale it a little bit further back. Now, mind you, this is all for reactors that keep running. This is not like NTR, not like NERVA, which is running just for, some minutes or an hour or something like that. So that is, we're talking about the reactor running for the full year. And we probably should get some distance between the habitat and the reactor. And this is the crew habitat radius. It might be quite wide. And then we have a safety margin. But anyway, let's go with this gas core reactor. Maybe gas core is rough. Particle bed reactor. Okay, but that's still obviously way off. I mean, we're basically shoving them into the reactor, it feels like. I'm not too sure that's good. But the problem is I have my primary material as steel. Steel's not good at this. Tungsten brings that all the way back down, but 113 millisieverts is still rough. The total mission dose budget includes the background radiation, and you can set that as the mission environment down here, cislunar, deep space cruise, Mars surface, and stuff like that. I don't know if its numbers are right. I don't like them because they are too high, but this elevated. But the thing is, they're probably higher than necessary because they seem to be measuring as if people are standing outside, perhaps in a spacesuit without any shielding whatsoever. So take the mission environment and the total mission dose with a grain of salt. The main thing that we want is this dose breakdown by source. So let's try and fix the dose here. And of course, we can just increase the thickness of the tungsten. And we get maybe, I can get it to 20 centimeters, and then maybe add some, I wanted 20. The function to type in a number might be nice. And then some additional borated polymer. How much does this all weigh once you do this? Well, we'll see in a sec. First, it is handy to get a sense of the geometry and this diagram. What you see is that our shielding is quite wide, right? The reactor is actually quite small right now for a 4.9 megawatt reactor. It's pretty good, and that's partly because it's this particle bed, which is top-notch. Gas core would be much larger, you can see. And then when we take a look at this diagram, the shielding is narrower out here because of that. This is meant for people doing Kerbal Space Program or sci-fi novels, or doing stuff fictional, or designing these spaceships for art or for games. This is not on the assumption that you're really doing it. I assume that those people are going to go ahead and know the equations and all the research and all that business. So this is for that level, and for that level I was satisfied with the numbers. So what we want to do is, with this diagram, narrow it down. We've already decided our reactor type and power level here. This conversion efficiency means how much of the thermal power gets turned into electricity, which means that's not being wasted. So if you see the radiation, let's go through radiation dose. Oh, well, it still radiates the stuff, so it doesn't really matter for the radiation, it seems, how much of it gets turned into electricity. The thermal power all has to be. We are not dealing much with the thermal management. If we increase this, the thermal management cost goes down. But I've got an entire other radiator designer and calculator that I'm working on. So if more of the thermal power gets turned into electricity, then less is needed for the thermal management. So, but we don't, this just gives a rough approximation. There's a whole other calculator for the thermal management instead. So we're focused on the radiation, not the radiators. This diagram will help us tighten this up. We can, instead of having this shield diameter, make it smaller. But then eventually the habitat is bigger than it. Well, I mean, it seems to go red a little bit late. So take a look at the little dotted line to judge instead of this habitat. I'll have to fix that, it looks like. So not such a final version after all. As we move the shield further out, that narrows it. So keep that in mind. So then we can see what the estimated mass of our shielding is, because that's the tungsten, borated polymer, and the current neutron shield, which is water. And we see that it's mostly the tungsten. Now in the diagram, the tungsten is covering more space. Perhaps I should split up the tungsten and the borated polymer layer. We can actually narrow the tungsten. But then the borated polymer looks like it needs to be wider. Borated polymer was not a big consideration in terms of mass. So yeah, I should probably split those up. There's a possible borated polymer layer here too, because it's mainly used for the neutron blocking. But overall, this is in a much better state and will give a good sense of things. And so we have a low radiation dose here. That's quite nice. Shows the radiation dose at the front of the habitat, middle of the habitat, and rear of the habitat. In case your habitat is a very different size, for instance, if we have crew habitat depth like 80 meters, so now it looks like this, pretty extreme. Well, in that case, the radiation dose is very different depending on where it is. So that shielding is not too bad. I mean, 16 megawatts is not the biggest fusion reactor ever, that's for sure. And we have here a 2.5 ton reactor mass for 16 megawatts. But that's for fusion. If you try to get that out of, let's say, the gas core, well, that's heavier, but not that much, really. And that should make sense. I mean, again, the Nerva cores, they operated at 1 gigawatt or more, but they were only meant to run for a short amount of time. If you need to contain all the fuel for like a year or more, then your reactor's got to be more like this 53 tons for 1 gigawatt instead of the massive Nerva, right? So that's the logic, and they'll be physically larger as well. Okay, so that's the reactor system designer for the radiation shielding, and hopefully it'll be useful to people. I'll link it in the video description. It does use some CSS stuff from the net in order to make the display proper, but other than that, I don't think it's connecting for any purposes. It's HTML, so you can look at the source code. So with that, thank you for watching. Hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.